Welcome again, everyone. Thanks for coming back. And so I'm going to be telling you a little bit about deep learning, and Don will also tell us more at some point. But before we get into deep learning, I think it's good to recap linear models, especially for those who just joined this session. So Don already did a great job telling us about them, but if you want to know a bit more, let's take an example. So say I'm going to write an app, and I want this app to be used by students who are trying to get into college, right? So I want them to give me their SAT scores and their school grades, and I want my app to be able to predict whether or not they're going to get accepted at the university of their choice. Sounds good? So how am I going to go about building this app? So I think to myself, let me get some data about the acceptance and rejectance from this university. So I go to last year's batch, last year's applicants, get all their scores and their outcomes, whether they got accepted or rejected, and I just put them on the scatter plot, right? So the blue points are the people who got accepted, and the red points are the people who got rejected. So this is good. Now I have a new student who's trying to use the app to find their outcome, to predict their outcome. So the student's grades are right here, where the question mark is. So just by intuition, logically speaking, do you think this guy will get accepted or rejected? Yeah. Accepted, right? Now to us, this is very easy, right? We can just look and see it. But we need to tell this computer or this app to do this work themselves. Now, how do we teach them to do this? In this case, we're lucky because the data looks very separated. It looks like you can separate the points by a straight line, right? Now, the equation of this line, Don showed us a bit about equations of lines. Let's not dwell on this right now, but we have the equation of the line, right? And so what I'm going to tell my app to do is to use this thing called a perceptron. So every new student that comes in, it's going to take the SAT score and their school grade, compute like basically a weighted sum of these quantities, and then check. Is this weighted sum positive? i.e., does this point fall on this side of the line? If that, then predict that yes, they will get accepted. If not, then they will get rejected, or at least that's what we predict. And that's basically the building block of artificial intelligence, this perceptron. It's very simple, but it's very effective. So the perceptron in artificial intelligence is very much like the neuron in the brain. So the neuron also is very simple. It just takes nervous impulses through the dendrites as input, and then does some processing with them, and then decides what to output through the axon, maybe to the next neuron, right? Now, also remember Don mentioned that sometimes I don't want this dogmatic hard cutoff, yes or no. Maybe I want my chances of getting accepted. So maybe I want the app to tell me you have a 90% chance of getting into this university instead of just saying yes and no, right? How do we do this? Can we still use a perceptron? Not quite, but almost. We can use this thing called logistic regression. It separates the points. So these are the points that are like indistinguishable. They're half-half probability. We don't know, you might or might not get accepted. Everything above the line has more than half probability, and below the line, less than half. And it works similar to the perceptron, same structure. So I'm going to take a weighted sum of the SAT score and the school grades. But instead of just seeing positive, negative, yes, no, I'm going to try to output a probability instead, which is your chance, some number between 0 and 1. Now, how do I do this? Especially because the weighted sum could be any number. It could be 500. It could be minus 20. How can I go from minus 20 to a probability? We use this thing called a sigmoid, which also Don talked about in the first session. So the sigmoid is this magic function. You just give it any number, and it will always return something between 0 and 1. And that makes sure that after I take the weighted average, I'm getting a probability. OK. Now, this is all good, but real life is not that simple, right? So when we get the scatter plot for the students from the past applicants, it might not be linearly separable. It might look something like this. So maybe no matter how high your SAT scores are, if your school grades are bad, you're still going to get rejected, or something like that. So what we really want to be able to do is we want to be able to fit nonlinear models as well in our data. And we've already seen a couple examples of this with the trees and KNN and so on. But now we want to focus on another goal. The goal is, can I use the linear model, this basic building block, the perceptron, in order to create a nonlinear model? Can we do this? The answer is actually yes. So basically, looking at this nonlinear region, you can kind of see how it could be a combination of these two, kind of, right? Like this segment and this segment could kind of combine to make this. So maybe we're onto something. So let's try to accomplish this goal. My goal is to get that nonlinear separation, right? But I'm going to start out with two linear models. So I'm focusing on this one student. The first model predicts that the student will get accepted with probability 0.7. The second model predicts the student will get accepted with probability 0.8. Now I want to kind of combine these two models with the goal of getting here, right? What's the easiest way to combine two numbers that you can think of? Just sum them up, right? Heck, I'm just going to sum them up. Okay. So 0.7 plus 0.8 is 1.5. I don't like this. Why not? Because 1.5 is not a probability. A probability has to be between 0 and 1. Okay, so are we doomed? Nope, we can use the sigmoid, right? You got it. So we can use the sigmoid. The sigmoid will convert our 1.5 to a nice number 0.82 between 0 and 1. And then we can output that. Okay, but what if I trust this model a lot more than I trust this one? Is there a way to tell this process, like prioritize this guy more? So we can just assign weights. I think I heard weights. So instead of taking a flat sum of 0.7, 0.8, I'm just going to take a weighted sum of the two predictions. It looks a bit ugly, but this is a weighted sum. And the outcome is 2.9. Again, it's not a probability, but no problem. Just apply the sigmoid. And then we get a number between 0 and 1. Now, if we do this process for all of the data points and try to see, okay, which points now are the boundary cases, the half-halves that were originally on the line. If you look at these points, they will actually be on this curve now. So this process actually succeeds at taking these two linear models and resulting in this nonlinear model. And remember, so we're going to tell the app to do this. So if we already have a perceptron for model 1 and a perceptron coded for model 2, what we just did is we just take the output of each perceptron and feed them both as inputs to a second perceptron. And this guy is going to average their predictions and output the final probability for us. And why stop here? Who's to say I can't kind of average out 3 linear models? And then when I do this process, these 3 regions combine to form this triangular nonlinear region. And basically, there is no limit to what we can do. We can even have multiple layers of linear models stacked up. One is the input of the next. And when we do this, we get more and more nonlinear regions here. So to recap, what we did is we started with the basic building block, which is the linear separator perceptron. And just by combining them in different ways, we're able to get more complicated predictions and more nonlinear models. And this is very much how the brain works as well, right? Your brain, the building block is a simple neuron, but when you stack these neurons one after the other, you get all these complicated functionalities that we have. Now, I kind of assumed it's easy to get this line, right? But let's go back to this process. So how do I train the perceptron? So I know I want to use a perceptron. It's just like, what numbers should I plug in here so that it's actually able to predict accurately? So to determine these numbers, we need to tune these numbers to the historical data that we observed, right? So we already have like 100 past applicants and their outcomes and their scores. We want to make sure our perceptron is able to accurately fit and predict these people. And that's how we're going to be choosing our weights. Okay, so what's the actual process? Well, we're going to start with a random guess. I'm just going to put like, I don't know, 1, 2, 3 here. It doesn't matter. I'm going to start with a random guess. And then after we take the random guess, oh, and there will be some equations on the slide. You don't have to worry about them. This is just if you're really mathematically inclined. But otherwise, just listen to the big picture. It's pretty good. So we're going to start with a random guess. And then we'll see how we're doing, right? So what does this mean? I'm going to just pick a point. So say I know that Robert applied last year. He had this score for the SAT and that score for his school grades, and he got accepted. So I'm going to plug in his SAT score and his school grades and see what my guess perceptron, how it's doing. Now say my guess perceptron says, oh, Rob has a 0.05 probability of getting accepted. So most likely rejected. Well, clearly this perceptron is way off because we know Rob got accepted, right? And so it seems our guess was not really that good. So maybe we should tweak these knobs a bit, the W1, W2, W3, to make the perceptron more accurate. If alternatively, every time we input something, it's guessing correctly, then we're good. We can just leave the weights as they are and move on, right? So to recap, we're going to plug in some historical SAT and school grades, and then we check the prediction at the output of the model. And then we're going to find the error, like how far off are we from the ground truth. And then based on this error, we're going to try to tweak the weights. And the most efficient way to tweak the weights so that we're not wasting time is to just move in the opposite direction to the gradient. So this is going back to Don's first discussion with the guitar tuning and so on. Now, the takeaway from this slide, ignoring all the stuff on, on the left side, is that I try a data point, see what error I get. Once I have an error, I actually have an equation that I can use to update the weights. Okay, error to weights. Okay, so this is fine for a single layer. But you know, with deep neural networks, you have multiple layers. I mean, in this case, I have 2, but we can have hundreds. So how can I do this process in that case? It's going to be pretty much the same. You start with guesses for all the weights, right? And then you plug in some data point, Rob's scores or something, and then check the output at the end. Now, if this were a single layer, we would know how to do this. We would just use this error and update the weights, just like we did in the previous slides, just use that equation. But now what do we do when we have multiple layers? So what we do is we're going to try and propagate this error backwards. I want to figure out who is responsible in this layer, which node is responsible for how much. I'm going to start assigning blame. Like, this is actually where 90% of the error is coming from, and these guys are maybe fine. So we do this. We propagate the error backwards, assigning blame to the previous nodes. And then at this point, we are done with processing that layer. And we're back again in the same problem of single layer updates. And again, we can invoke the same equation. So the moral of the story here is if we know how to do it for one layer, when we have multiple layers, we just reduce the problem to multiple single layers. Now, I have good news, which is in practice, we don't even need to bother writing these equations and these updates ourselves. In practice, we use a package, something like Keras, TensorFlow, or something like that. We just tell the package, I want to use a neural network with, I don't know, 10 layers, and I want 500 nodes in each layer. I don't know, we can choose anything. And then we give it the data, and it does all the learning for us. It will determine, with a simple function call, what the optimal weights should be. So this was just to give you an idea how it works, but in practice, we rarely have to write these equations ourselves. Okay, so I can see that maybe we're done with equations. So I'm going to hand this off to Don, who will show us a demo of how all this actually works.
We're going to use a different data set now than the flowers. The flowers was too easy. So we're going to use handwritten digits. And this is a data set from NIST. And I'll show you what it looks like. I had to restart. Let me get this back. Python, CH12. First time you start Python, it takes a little while. Unlike Iris, I'm sure. Okay, so this is our challenge. So our challenge is to recognize handwritten digits. Okay? So you are given, so imagine you're writing the program. You're given pixel values for, these are 28 by 28 pixel values. Each value is a grayscale number between 0 and 255, and you have to write a program to tell me when I give you those 728 numbers, 720, 748, something like that. What is it? 728. 728 numbers, what the digit is. Funny story on the 728. So I went to some bar, and they had like a quiz night. And the first question was, what is 28 squared? Now, I would not ordinarily know that, but I had just taught this that day. And I said 728, and the guy thought I was a genius. I was like, what are the odds of getting that question that night? How would you write a program like this? Does anybody? I mean, I have no idea how I would do that, you know, to recognize a digit. You'd search for lines. You'd find the edges. I mean, it'd be I think, a very difficult program to write. But actually, just using these simple machine learning techniques, what maybe should be simple to you now, you can actually write this program with an incredible accuracy. So let me show you how to do it. This is just one more thing about the data set. There's basically, this data set is 50,000 handwritten digits. Some students were tasked to do this. And here are like the first 25 sevens. And you can see, even if you had your logic, you might forget how people write sevens. Some people do a cross in the middle of the 7, you know, like this. Some people do a little cap like that. You know, some people just do the two lines. So there's variation in the way people do 7s as well, right? And that includes other numbers also. So how would you do that? So we're going to solve this twice. We're going to solve it first with logistic regression. So you can actually use linear separation on this. So just the same techniques we used before. 784, that's what it's 784. See, if I went into the bar now, I would get it wrong. So all the pixels are 0 to 255. We scale it to between -1 and 1. Machine learning algorithms love things that center on 0. So there's usually a lot of rescaling of features. Each instance has a class between 0 to 9. So there's 10 classes here versus the 3 flowers, basically. And there's 60,000 training instances, 10,000 testing instances where you use the testing. Okay, so logistic regression. I was too lazy to make slides, so sometimes I just write. But you could think of it using kind of Aliaa's model as these 784 features, plus a 1 on top, 785 weights to multiply by those features. Then you do the sigmoid, which is the SPI character. And then you have the probability. This is one model. I'm training it whether it's a 7 or not. The probability that that's a 7. And you would elaborate that for all 10 digits, 0 through 9. So essentially, you have 10 different models, all with their different under weights. So you have 7,800, you guys could do the math, add a 0 at the end, weights that it's training. Okay? So it's training. It takes too long, actually. As opposed to what I showed in part 1, I have to pre-record these. So I'll hit the movie. This will run. I forget how long it takes. It takes about a half hour, if I recall. And the accuracy is right there. So logistic regression, what I've taught you before, will give you 92% accuracy on handwritten digits. So that's it. Essentially, 18 lines of code you know, you can write plus 60,000 training demo. This is why machine learning needs data. The algorithms can be quite simple. So you have this 18 lines of code plus 60,000 data elements, and you can write a program, at least for me, and you're probably better engineers than I am, I would have no idea how to write. And you can get this thing to be pretty accurate. This is when I really got to like machine learning, when I figured this, when I went through this. So here are the 25 instances with logistic regression to get a feel for how good it is. And you can see 23 of these are right. I'm just loving this pointing thing. 23 of these are right. This one's wrong. T means the target, the right answer, and P means the prediction. So it thought that was a 1, and it thought that was a 6. So you can, at least in the 6 case, the 5, you can see how it gets a little confused the way this person wrote this. But the rest of them it got right with this algorithm. Here are the first 25 that it got wrong. Okay, so you can see the 9 and the 5. But you can see the others. I don't know what this is. I guess that's a 5. That's what the student said. You know, a lot of these students, they're not that good, you know. Not everybody gets A's, you know, in school. But that's another thing you get, of course. When you train, you have to think about the data that you're training the algorithm on. Like, you know, when you think of clinical algorithms and you train it all on your clinical data, the best you'll come up with is the average doctor, essentially, or the average decision maker. So, so that's another thing to think about is curating the training data, because these machine learning algorithms are basically going to just try and repeat what the training data is saying. Okay, so now back to Aliaa stuff. Now we're going to use a neural network. So this, I didn't write a picture of it, but it has 2 hidden layers in the middle of 50 cells each. So you have the beginning, 785. You have 2 hidden layers, and then you have the 10 digits on the end. And I'll fast forward. I think this one only takes 40 minutes because the library is so good. And what do we get? 96% accuracy with a neural network. And in this case, let me pause it so it's not distracted. It's running again, my little movie. In that case, there is 42,000 weights, in a sense. Not in a sense, actually. So you have your input cells, and then 2 hidden layers of 50. 50 weights getting to the first layer, 50 weights from the one middle layer to the other layer, and 50 to 10 cells in the end, the 10 right answers. So, so it trains 42,000 weights. So you can see how you can all of a sudden get millions of weights. This is a coarse-grained image, 28 by 28, but imagine these radiology machine learning things with these CTs and, you know, very high-res images. So the other thing you can imagine, actually, the other thing you can imagine is the compute power that's really necessary to calculate so many weights so quickly. And you can also see it's a lot of matrix math, because you're doing multiplication from left to right to predict the digits, and then you're doing this backpropagation, which is a lot of matrix math. So that's why these machine learning architectures are parallel computing, because you can do a lot of matrix math in parallel. You sort of divide up the matrix and have it do its work and then collect at the end. Okay, so we get 96% accuracy there. And let's take a look at the first 25 digits. In this case, it got 24 of them right. You can see this, the 9 it got right, and then this one it still gets wrong, which is a tough one. And this is the first 25 that it got wrong. And we as humans can get these right, you know, so it's a pretty good network. I mean, maybe good enough for the post office, like if you're writing something to recognize zip codes and throw things in the right bins type of thing. You know, it depends on your use cases. Oh, here, I did draw this out. So this is essentially what these 42,000 weights look like and where they're arranged. So you can see you have your feature dimension. You have your output, your 10 digits. And then in that model, 2 hidden layers of 50 each. Like Aliaa said, you could have a dozen layers, hundreds of layers. It's just really compute time and those sorts of things to make choices like that in your architecture. Somebody was asking me about the magic of machine learning. Like they heard it was magical and mysterious and those sorts of things. And I'm sure you're gathering that it's not. It's quite mathematical, the way this actually works. But the only little piece of magic, I would say, is this notion of a hidden layer and what the values of these cells actually really are. Because if you think of a cell here, you know what it is. This is the grayscale value of such and such pixel. And if you think of a cell here, you know what that is. That's the probability that this is an 8, according to these weights. But God knows what this cell is doing, essentially. It's sort of the net result of a lot of backpropagation and adjusting the weight. And this cell is coming to some intermediate conclusion, in a sense, between the original cells and the 8. And it's actually a little bit the way your brain works. So when you see the letter 8, you see a circle on top of a circle, in a sense. So when you see the letter 7, you see a horizontal line and a diagonal line. So I mean, it's all instinctive now, but when you're an infant, let's say, when you're learning something, you have a intermediateness between the pixels of your eye and your conclusion that this is a certain number. And another example would be reading a sentence. You know, you look at the letters, you build it into words, then you sort of make sense of the sentence, and then you might have a certain mood about it, you know, that kind of thing. So there's kind of an intermediateness between the detail of the pixels and your final conclusion. So that's one way to think of the hidden layers from a brain point of view. But there are techniques to focus what the hidden layers are actually thinking about and working on. And for this, I'll turn it back to Aliaa to talk about the convolutional neural network, which is a particular kind of neural network that we use in images. And then I'll go back and show you how that does on the digits.
All right, sorry about that. So the techniques we saw so far are not necessarily the best for image recognition. And here's the reason. So recall what we did with Don's example. So we had this 28 by 28 pixel image. We just turned this matrix into a vector of length 784. So we just flattened all these pixels next to each other. And then we stacked on the layers, right? And every hidden node in a layer is connected to all 784 of the pixels. So that quickly blows up. Like every one of these edges is a weight that we need to learn. And so if my hidden layers had 500 nodes each, which is actually a reasonable choice, some people do this, you would end up with over 500,000 parameters for just this simple task, which is 28 by 28 pixel. So as Don was saying, if you have radiology or like more complicated images, then this is just not tractable. The other thing is that by flattening the matrix into this vector, we are ignoring all the spatial information that's in this arrangement of the pixels. So all these correlations are lost, and the network has to learn them from scratch, which is very redundant. This is why we have convolutional neural networks, and they are specialized for images. What they do is that instead of connecting every hidden layer, every hidden node to every single pixel in the image, it kind of asks each node to specialize in one small region of the image. So like this node, for example, might be looking for an eye in this region, and this node's looking for an eye in that region. And that immediately shrinks the number of parameters dramatically, right? So just break it down into small subregions. Now, something else that can help us reduce the parameters is this. If all of these nodes are just looking for an eye in the image, is there a reason why they should have different parameters? They're all looking for the same thing. An eye is an eye, whether it appears in the upper corner or the lower corner, right? So then, instead of having different parameters for these guys, let them just share the same set of parameters. And this, again, reduces your number of parameters that you have to learn dramatically. So let me skip this. So here's how it works. I'm just showing you now the architecture. So we have an input layer. The input layer has the letter 7, the number 7 in pixels. Say this hidden node is looking for horizontal edges in my image. So it's only going to look for a horizontal edge in this square. And that's it. That's what it ends for this node. And then we have a second node that also looks for a horizontal edge, but in this square. And we keep doing this until we cover the whole image. So this layer is specialized in looking for horizontal edges. We call it a feature map. We can have other feature maps for vertical edges, and so on. And then we combine the results of these feature maps, and I'm abstracting here the details, but you'll get at the output, it's a 7. Now, one thing I want to emphasize here is that we do not actually tell the network what features to look for. So we don't tell it to go look for a horizontal edge or a circle or something. The network learns by itself what the optimal patterns to look for are. So we just give it a whole lot of data, and with the backpropagation, when we come back and check, oh, what are these hidden layers doing? We find that they naturally converged on their own to start looking for these meaningful patterns. So it's really cool. So this is what a convolutional network would look like. It would be an input layer, and then you have a bunch of convolutional layers. Then you have something called a pooling layer, which really just summarizes the results of the previous stuff. And so on. You can stack as many of these as you think is good for you. So if we're trying to understand what's actually going on in these networks, usually it's something like this. You start with an image that has spatial information, just a bunch of pixels next to each other. And as you go through the layers of the network, you gradually try to get rid of spatial information and instead gain understanding of concepts instead of pixels. So the first layer, you could be looking for simple features like edge, diagonal, so on. And the next layer, you could be looking for contours and so on. And then by the end, when you've reached the output, you don't have any pixel kind of logic left. All you have is concepts like, is this a wheel? Is this a cat? Is this a bird or something? And again, as Don mentioned, this is how it works in the brain. So when an image hits your eyes, it first goes to the cortex. And then every cell in the cortex specializes in only one tiny region of the image. And then combined, they cover the whole image. And they do very simple processing. And the first layers are just detecting very simple features like edges and so on. And then they pass on their result, their output, to the next layer. The next layer does something more complicated. And this keeps going on until finally, when it's time for you to make decisions or think or, in deeper layers of your brain, you just have concepts left. So you can think, oh, this is a cat. Oh, so now I'm going to hand this back to Don, who will show us how CNNs do on the problem we're working on.
A drama in my presentation, so that's why it's not 2 times we're going to solve it, it's 3 times. You can see I've crossed it off. Okay, so we had logistic regression, a simple linear separation. We had a fully connected neural network. That was the first one, where every hidden layer was fully connected. And now we'll do it with the CNN, which is what Aliaa just described, where each of those hidden layers, the middle cells, will just be connected to a portion of the image. So we're kind of telling those hidden layers, just focus on the upper left corner, just focus on the upper right corner, that kind of thing. So let's see how it does. This does 20 runs through the data. Could be on pause. Okay, and it got 99.4% accuracy, basically. So a CNN, again, same kind of theory, but by focusing these hidden layer cells, it increases the accuracy significantly. So, for example, the first 25 digits, it got right. So it gets all these correct. And then it actually gets the next 150 right. And I didn't actually count the first one it got wrong, but it does quite a good job sort of sweeping through the data set and getting it really, really accurate. So this is a really great kind of use case for a really great architectural design. So you can see linear classifier got 92%, which I think is pretty good for 18 lines of code, actually. Feed-forward neural network, so fully connected network was the 96, and then the CNN is the 99. Okay? So, you know, we're going to have time to do the transfer learning, if you want to do that. Yeah, we do, if you want. Okay. So let me say a couple of things, and we'll cover one more topic, because we have a little bit of time. So one is, there are more kinds of networks than the CNN. So these are basic, I mean, I'm sure somebody was trying to like elaborate everything they've ever heard of. But these are just different neural network architectures. And the concept is the same. The building block is that logistic regression, the sigmoid function, a linear equation, and then connected to the next layer, which essentially the multiple layers makes it nonlinear, like Aliaa said. But there are two very popular ones. So the CNN is the one for images, essentially. And it's also used for text by, instead of focusing on a section of an image, it it'll move through a paragraph 4 words at a time, in a sense. And it'll sort of use the adjoining words together to train hidden layers. So CNN is also used for text, but it's most famously for images. And then the other one is a LSTM. The keynote guy mentioned this one, and Babek mentioned this one. This is a flavor of a recurrent neural network. And I don't walk through an example. Maybe next year we'll go into part 3. But this is for data sets that have some flow to it. So text is an example. So there are neural networks that can write Shakespeare. Actually, in a book I did, we wrote Shakespeare. You feed it a lot of Shakespeare, essentially predicts the next word or the next sentence based on the last sentence. So there's a flow in the way we write and the way we speak. And each word, what you're about to say, depends on what you have just said. So the recurrent neural network, instead of just training on each instance, also has a bit of memory. So it both trains on the next word you say, but has memory for the last word you said. So that's why the cells loop back on themselves. Where's the picture of it? It's right there. The cells, both of these, this is a style of that. The cells sort of train on the new instance and their old value. So they have a bit of memory, in a sense. So if you're using a neural network to play music, what we just saw in the keynote, to write stories, and even type ahead. So on your phone, when it's predicting your next word, those, if they say they're using AI, they're using that, an LSTM. So a network that has a bit of flow and memory to it. Okay? And it's quite amazing. I mean, I thought that keynote was amazing. And there's actually a short movie that was completely written by a machine learning algorithm. You know the star of Silicon Valley, Thomas Middleditch? If you Google him, you'll find a short movie. I forget what it's called. And the entire script is from a machine learning algorithm. It really makes no sense, actually. But it makes a little bit more sense than you'd think. Like 10 years plus, plus 10 years or plus 5 years, this might be something. So it's pretty interesting. And then maybe I'll close then on a couple topics. So one is we're in the AI machine learning buzz, even though it's 50 years old. So the reason this happened was actually this contest, or a key reason was this contest. So ImageNet, ImageNet was this annual contest where there were 1 million images, and you had to write a program to guess what the image was. Okay? This actually started in 2005, I think, but I just have 2010 and beyond. So we were like at 30% inaccuracy or more for years and years. Machine learning's been around for 50 years. So we were, we were up here, basically. This was the first use of a CNN. So all of a sudden, it dropped to 15% from being a 25, 30, 35%. It all of a sudden dropped. And the next year, down at 9%. And then the next year, so getting right in 3 years' time or so, what is that? 1, 2, 3, 4 years' time, we were beating humans, basically. And it was really the CNN breakthrough, this particular architecture that really drove that down. So if you're wondering, when did this crazy buzz start around machine learning? It was basically around that. A few years ago, when this classic problem of telling a dog from a cat or recognizing an image essentially got solved. Okay? So if the algorithms have been around for 50 years, what is the breakthrough now? Like, why are we all of a sudden using it? So one is the algorithms did get a little bit better, like I said, with CNN. But the other is data. So did we have labeled images 50 years ago? Pre-Facebook? Not really. So now we have labeled images. And if you look at clinical data, we have EMRs now. We didn't have EMRs 15 years ago. Now we have all this codified clinical data. So the data is here. Like if you think of the magic of the handwritten digits algorithm, it's only that 18 lines of code. But the magic is really the 60,000 training points. It's those students that put in that data. So that's really the importance. That's why we like the business we're in, the importance of sort of cleaning up and aggregating, normalizing data, because these algorithms need data or they don't work at all. So now we have digitized data, like labeled images. How does Google Translate work? It works because the UN issues documents in all these different languages that say the same thing. And Google Translate can now eat those things up, and it works. So data is really newish the past decade or two. And the compute architectures. So this notion of training 1 million weights and doing it in your lifetime wasn't that possible. But now with sort of GPUs, parallel architecture, sort of handwritten CPUs that do matrix math, and that's basically all they do. Now you can really train these things in a reasonable period of time. That plus some breakthroughs on the algorithms itself sort of have created the possibility of machine learning that we know today. So that concludes our 2 parts. To do a bit of a recap, we covered the most popular area of machine learning called classification. There are a couple different areas, actually. That'll be next year, too. But this is the notion of using features, figuring out the function that you apply to those features to come up with a class, a digit, whether the person has cancer or not, whether they're going to get readmitted or not, whether it's a Setosa flower or not. That's classification. And then we covered these approaches: linear, decision tree, KNN, ensemble, and then sort of deep learning. So that's it. I'll thank Aliaa for helping me out, and happy to answer any questions throughout the day. We're actually done with time on this session. But thanks, everyone.